Ohm's law and Jules law. These are the two fundamental equations that circuit builders will be using all day, every day practically, to figure out what resistors they need, to figure out what currents will be flowing through devices, to figure out how much power devices will be using to make sure they're keeping under power limits, and to see what size heat sinks they have to put on heavier components. They are incredibly simple, just basic algebra, so we'll go over the math very quickly, and then we'll do some quick demonstrations. Now, Ohm's law and Joule's law don't take just one form. They're a lot more complicated and perhaps interesting in their theoretical forms they were derived in, but we're using the ones that are practical for actually building circuits to avoid unnecessary detail. Ohm's law, as used in circuit building, is voltage equals current times resistance. Now, this applies over individual components, such as a single resistor, as well as the circuit as a whole. Some devices are non-ohmic, as in they don't obey this rule directly. Diodes, like LEDs, and transistors are the primary example of this. Another example would be a fan. But even in those cases, you can calculate an effective resistance because they will have certain current draws. A diode, for example, has a forward voltage drop, so you can take that voltage out of that part of the circuit, calculate the resistance remaining using Ohm's law, and then you get the total current throughout that part of the circuit, which you can then put back into Ohm's law to calculate the effective resistance. Not the real resistance, but basically how much it is in practice. If you want to find current, you divide the resistance over. So current equals voltage divided by resistance. We just divided the R over. And the other way, resistance equals, now we're dividing the I over, voltage divided by current. So it just depends on which things you know. This is probably the most common version. You know your input voltage because you know a certain power supply. You know what your other devices need, such as USB input is 5 volts. You might have 3.3 from a power rail in a laptop, that sort of thing. And you also know the current, for example, an LED. So you know what amount of current you want flowing through that part of the circuit. You're calculating the resistance that you want left over. Let's say we have our battery, we have a resistor, and we have an LED. Simple circuit. The battery is providing a certain amount of voltage we know already. The LED drops a certain amount of voltage we know already. The brightness of the LED is determined by the current going through because the forward voltage drop, while it does vary with the current, it doesn't vary much. So we just assume it's a fixed value. So we decide how much current we want going through here. That determines the brightness. And then we have a resistor value. So this is our V. This gives us our I, which tells us our R. So let's say we have a 9-volt battery. So let's say the forward voltage drop here is 3 volts. So we have 6 volts left over. This is a drop. So let's say negative. So the battery is supplying 9 volts. The LED is dropping 3 volts. And that leaves 6 volts here. This is using something called Kirchhoff's voltage law. We'll get to that in the future. It's another simple bit of math, though not as simple as this. It involves linear algebra. So let's say we've decided that we want 3 milliamps to run through this diode. And again, Kirchhoff's current law, the whole thing, well, Kirchhoff's current law and common sense say that the current is going to be the same through all 3 devices. So we have 6 volts divided by 3 milliamps gives us what resistance to put there. This form is useful when you know the effective resistance of something and your voltage input and you want to see how much current is going to be flowing through. Usually more of a diagnostic tool. It's useful for analyzing a circuit you did not make, such as if you have an LED circuit in something else and you want to see how much current will be flowing through, then you just figure out how much voltage is going into the circuit, use your multimeter across the resistor, And you can calculate the amperage without having to disassemble the circuit. Because remember, to measure amperage using a multimeter, you have to put your multimeter into the circuit, which is not always practical. This form is, of course, much less common because most circuits are going to have their voltage set very early on. You're going to decide on what kind of device you're making. That's going to tell you about what power. But it can be useful to decide, for example, how many batteries you need in your pack. Now we have Jules Law. Again, this is the Jules Law form that is useful for circuit building. Jules Law is in all kinds of different forms based on different parts of physics. Power. This is watts. This is like what your power company charges you based on. This is what your power supply on your computer provides. Power equals voltage times current. You'll notice that resistance is not included. Well, it's very simple. If you have voltage and current, then you know the resistance. Now, that includes effective resistance, which is another reason resistance is not directly included, because this works for ohmic and non-ohmic devices. No matter how the voltage and current are determined, whether it's a diode voltage drop or an ohmic resistor or anything, you know the voltage and current. That's the physical thing going on. You know how much power. Power is important for two reasons. It's important because you need to make sure that you can supply that much power from the wall, or from your battery pack, or wherever. And second, it's important because power involves heat dissipation. Nothing's perfect. Every circuit, everything is going to dissipate some heat, and that can melt delicate traces or straight up blow things apart. So every component in every circuit will have a power limitation that it can accept. And so you use these equations to make sure you're not going over that. Now let me write Ohm's law once again. So there's Ohm's law again. Now why did I do that? Well, first of all, if you are dealing with ohmic devices, such as you want to make sure not too much power is going over your resistor, you can put this equation in different forms. What if you're not sure how much current? What if you want to just see voltage and resistance? So voltage, but current is voltage over resistance. See? And simple algebra. So instead of calculating power based on voltage and current, you can calculate power based on voltage and resistance. Or substitute in for voltage is current times resistance. Current times resistance. And then current again, because we're substituting for V here and we still have the I. So now we have I squared times R. So power is square of the current times resistance. Now this might initially be interesting. In this one, increasing the resistance decreases the power consumption. In this one, increasing the resistance increases the power consumption. Why is that happening? Well, in this one, if you increase the resistance but keep the voltage constant, right? Because if you're changing both, then you're getting all kinds of crazy numbers. We increase resistance but keep the voltage constant. In order to do that, then we have to let the current drop. Because see here, if we increase resistance in Ohm's law, and we want to keep the voltage the same, we have to decrease the current it's being multiplied by. Otherwise, increasing resistance would increase the voltage for the same current. So that's why that happens. What about here? If you increase the resistance and keep the current the same, that means you have to increase voltage. Increase resistance, but keep the current the same, voltage goes up. Because resistance increasing drops current at the same voltage. So you have to raise the voltage to compensate. This is why you have to actually analyze the math instead of just glancing at it. The math absolutely does directly correlate with the physical properties, but the straightforward human mind doesn't always figure that out. Because we think resistance reduces things happening in a circuit, and it does. But you have to think of the interactions, and the interactions can get buried. If all you do is memorize these little pieces here, print them out on a piece of paper and just hold them up in front of the camera, then you're not really thinking about it anymore. But the nice part of it is, if you think about it once, and then write it down, you don't have to think about it again. You can trust that you figured it out before. This is how peer-reviewed research works. People analyze and check it, scour it, make sure it's right, and then they say, okay, it's good. And now you don't have to look at that proof every time. You can just say, all right, here's the result. Now let's use it. Same thing here. Go through this analysis once in your life. It's like the Pythagorean theorem. Once in your life, look at all the geometry and figure out why it works. And then once you're confident, okay, this makes sense. Now you can just forget all that and say, okay, well, a squared plus b squared equals c squared. Now, one more quick thing. One common thing is to make sure you are not exceeding the power level for a particular component, such as a resistor. The resistors I buy are a very common variety used by hobbyists everywhere. 1/4 watt. They are good quality, but cheap, plentiful. And for low power circuits like messing around with Arduinos and LEDs, it is more than enough, because we are dealing in milliamps. But let's say we have a circuit, and we want to figure out if the resistor is getting too much. So we know the resistance of the resistor. So let's say we're doing part of a circuit that is mostly a control signal. It doesn't matter how much current is going through as long as it's small enough. So let's say our simple part of a circuit is the input to a transistor, sort of like an on-off switch. The amount of current is only minimally important. What matters is the voltage. So we have a voltage in, which is whether we want the transistor to be on and off. And then we have a resistor that's going to limit the current. So the resistor is dropping that whole portion of the voltage. So we know the voltage and we know the power. In this case, 0.25 watts. Let's say we have a 5-volt input signal. So we know that we want a certain power. We have a certain voltage, but we need the resistance. So we look down here. What involves power, voltage, and resistance? So we can just modify this equation. So if we multiply the resistance over, divide the power over, we get R, the resistance, equals voltage squared over the power. Basically swap the P and R. So now, if you know the voltage that's coming in and you know the maximum amount of power you want to go through, you can say, what is the smallest resistor that I can use that's going to give me that level of power? Because if you increase the resistor, then you're going to get less power. So this is giving you a boundary. You can say it can be no smaller than this. So if you need a certain minimum current, then you can just use the full power resistor. Or if you want to deliberately limit the total power usage of your circuit, for example, you're making a low power device such as something to be worn on the body, like a little blinking light setup that's sewn into your clothes. Then you can try and minimize the power and get the resistor value and then see what current you get, because then you have the voltage and resistance. You can calculate the current to make sure, let's say, whatever device is plugged in after requires a certain minimum current. So you could then use this equation. You just take these equations and go back and forth until you get the thing you want. So first we would do a quick demonstration of Ohm's law. So I have here a simple circuit. This is a 10,000 ohm resistor, and I'm using a maximum of 5 volts in my power supply. Positive power to one end of the resistor, the other end of the resistor to the positive of the LED, the negative of the LED to the negative power, and turn up the current. So it goes immediately to 5 volts and it's providing less than 1 milliamp. So how can we figure this out? So let's measure the actual amperage here. So I'm going to connect my negative probe into negative power, my positive probe into the LED. And I'm getting 239 microamps. So let's say the 239 microamps is how much current we want flowing through the circuit. Now we have to measure the voltage. So let me put the circuit back to make it independent again. So now it will light up on its own. And the current is slightly changed because there's a different amount of resistance, but it should be less than an ohm or so. So now we'll measure the voltage. We're measuring the voltage drop across the LED. So plug it in here. And we're getting a negative because I've plugged it in backwards. So we have 2.58 volts out of 5 being dropped by this LED. So we know our volts, which is 2.58. We know our amps, which is 239 divided by 1,000 divided by 1,000 because it's microamps. So 2.58 divided by 239 divided by 1,000 divided by 1,000 comes out to be about I don't know if the glare's too much, about 10,000 ohms. In fact, it's 10,794.979 ohms. There are some inaccuracies built into using a cheap Chinese power supply. But that's a simple demonstration of Ohm's law. Let's demonstrate Jules' law, the power. Remember to turn your power down when you disassemble your circuit so you don't touch something you don't want to touch. So now, I'm going to get a resistor that is 1 ohm. Why am I doing this? To make the math easier. These resistors are rated for 1/4 of a watt. According to Jules' law, if I put 1 volt and 1 amp across a resistor, I will get 1 watt. According to Jules' law, if I have 1 amp across a 1 ohm resistor, I need 1 volt. Lots and lots of ones. So if I have 1 volt and I put it across this resistor, like so, and like so, make sure the leads don't touch. Let's bend the legs out a bit. We now have a lovely little resistor that is about to have 1/4 of a watt to go through it. If I set this current limit to 1 amp, I should get 1 volt. So let's set it to 0.5 actually. 1 ohm, 1 amp, 1 volt. So if I want to make this 0.25, so I'm actually going to set the current to 0.5 amps, which will be 0.5 volts. 0.5 times 0.5 is 0.25. So half an amp should give me half a volt. So 1/4 of a watt is now going across this resistor, right here. So that's nice. So since I don't have a meter that can measure the actual power to demonstrate the equations, we'll instead do a practical demonstration. So, did you see that little puff of smoke? That was your resistor dying. And now you'll see, I can smell, you don't see much wrong with this resistor. Every component fails in its own way. Some of them tend to go loudly and some of them quietly. But you will see that now it is limiting the current to 12 milliamps because the resistor is no longer effectively resisting. Let's try something else. And by something else, I mean another 1 ohm resistor. Let's see if we have better luck this time. Let's see what happens. About the same thing. And this one is down to 6 milliamps. So let's try one more time. Let's do it a little more slowly. Perhaps it is the speed with which I am increasing the amperage that is causing the rapid failure. And if you're worried about me wasting money right now, each of these resistors, because you buy them in a pack, each of these resistors costs less than 1 cent. So it's okay. So let's turn it up to 1 amp, which is 4 times its normal allotted power. Nothing spectacular. But you can tell the fan in my power supply is going crazy because it's putting through a noticeable amount of power. Let's try 2 amps. So it's still providing 2 amps. It's gone up to 2 volts. Oh, we're getting some smoke. Let's try 3. There we are. And to not set off my smoke detectors, there we go. And now, if you look at the resistor, you'll see it's actually charred. And presumably, if I left it on there at 2 to 3 amps, it would have perhaps burst. So you can see sometimes you get a different failure profile based on whether you're getting a quick short circuit from something else in your circuit blowing, or whether you're just going overboard. So there is certainly wiggle room in the maximum power of the resistor. It can take more than 1/4 of a watt, but it's going to reduce its maximum lifetime. Just like if you overvolt your CPU with adequate cooling, it's going to work just fine, but your CPU is going to die early. So even though it's functioning, it's not functioning well. 1/4 watt is the number they give you that you should be aiming for to keep that resistor going for the lifetime of the device. So always obey your power limits. So that is basically all of the math you need to know to build very simple circuits, as long as you're following good directions. In order to build more complex ones where you have to analyze the flow pattern of current throughout the device, that's only half the math you need. The other half is by Kirchhoff, and lately by Maxwell. But Kirchhoff's versions are the simple ones we'll be going over. You don't need Maxwell's unless you're a physicist. So brush up on your grade school algebra and you'll be fine. Remember to follow the power limits of your devices, because you don't want to let the magic smoke out. And while this room clears of its campfire smell, I'll be seeing you.